Dependent events. Welcome, everyone. Today, we are going to expand our understanding of probability by moving beyond what we have already mastered. Up to this point, we have spent a lot of time exploring independent events, those specific situations where the outcome of one event has absolutely no impact or influence on the probability of another event occurring. You are likely very comfortable with that concept. However, as we move into more complex territory, we must recognize that in many real-world scenarios, events are actually linked or interconnected. This brings us to our main topic for today, dependent events. Specifically, we are looking at instances where the occurrence of one event actually changes the likelihood of another event happening. Over the next few slides, we will look at how to identify these links mathematically and how to calculate them using a concrete example. Conceptual understanding. First, think about it this way. Two events are considered dependent if knowing that one event has already occurred gives you new information that changes the probability of the second event happening. It's all about how much new information you have. To put this in much simpler terms, you can think of it as the first event changing the game for the second event. If event E occurs, the rules or the landscape for event F are no longer the same as they were before. This dependency usually happens because the conditions for the second event are physically or mathematically modified by the outcome of the first. As we are going to see in the next few slides, especially when we look at the mathematical definitions and the marble example, the first event actually alters the underlying setup, which is why the probabilities shift. Now that we've established the difference between independent and dependent events in our previous slide, let's dive deeper into the conceptual understanding of what dependency actually looks like in practice. Mathematical definition. Now that we have a conceptual grasp of what it means for events to be linked, let's look at the formal mathematical definition. This is where we move from the idea of changing the game to using precise notation to prove that dependency actually exists. Mathematically speaking, we define two events, E and F, as dependent if they fail to satisfy the multiplication rule that we use for independent events. Specifically, you can prove dependency if the probability of E intersection F, which is the probability of both events occurring together, is not equal to the probability of E multiplied by the probability of F. If that equation doesn't balance, you know the events are influencing one another. Alternatively, we can use the language of conditional probability to see this in action. Events are dependent if the probability of F, given that E has already occurred, is not equal to the original marginal probability of F. This assumes, of course, that the probability of E is not zero. Similarly, it would be true if the probability of E, given F, is not equal to the original probability of E, provided the probability of F is not zero. Essentially, what these formulas are telling us is that the conditional probability, the updated likelihood of an event after we have new information, is different from the original or marginal probability we started with. In the next slide, we are going to apply these exact formulas to a practical example involving marbles to see this math in a real-world scenario. Real-world example, sampling without replacement. Now that we have established the mathematical definition of dependency, let's move from theory to a practical application. The most common way you will encounter dependent events in your exams is through a process called sampling without replacement. This simply means that once you pick an item from a group, you do not put it back before the next pick. To make this concrete, let's look at a specific scenario. Imagine you have a bag containing 5 marbles in total. 3 of them are red and 2 are blue. We are going to perform an experiment where we draw 2 marbles, one after the other, and crucially, we do not replace the first marble before drawing the second. To analyze this using the notation we saw on the previous slide, let's define our 2 events. We will let E represent the event where the first marble drawn is red. Then, we will let F represent the event where the second marble drawn is also red. As we move into the next slide, we are going to calculate exactly how the first draw changes the probabilities for the second draw. Step-by-step analysis. Now that we have set up our scenario with the red and blue marbles, let's walk through the mathematical analysis step by step to prove that these events are indeed dependent. First, let's look at step 1, where we calculate the probability of our first event, which we'll call E since we started with 3 red marbles out of a total of 5. The probability of drawing a red marble on the first try is 3/5. Moving to step 2, we need to find the conditional probability of event F, given that event E has already happened. This is where the without replacement part becomes crucial. If we successfully drew a red marble and kept it out of the bag, we are left with only 2 red marbles, and our total count in the bag has dropped to 4. Therefore, the probability of the second marble being red, given the first was red, is 2/4, which simplifies to 1/2. In step 3, we calculate the joint probability, which is the probability of both events E and F happening together, written as P of E intersection F. To do this, we use the general multiplication rule we discussed earlier. We multiply the probability of the first event by the conditional probability of the second. So, 3/5 multiplied by 1/2 gives us a joint probability of 3/10. Now, step 4 is a bit more involved. We need to determine the marginal probability of event F, which is the overall probability that the second marble is red, regardless of what happened first. To find this, we have to account for both possible paths. Either the first marble was red or the first marble was blue. We calculate the probability of the first being red and the second being red, and add it to the probability of the first being blue and the second being red. Mathematically, that is the probability of E times the probability of F given E, plus the probability of E complement times the probability of F given E complement. When we plug in our numbers, we get 3/5 times 2/4, plus 2/5 times 3/4. This results in 6/20 plus 6/20, which totals 12/20, simplifying down to 3/5. Finally, in step 5, we perform the actual test for independence. We check if the joint probability we found in step 3 is equal to the product of the individual probabilities of E and F. We take the probability of E, which is 3/5, and multiply it by the probability of F, which is also 3/5. This gives us 9/25. When we compare our results, we see that 3/10 is not equal to 9/25. Because this equality fails, we have mathematical proof that the condition for independence is not met. Therefore, our conclusion is clear. Events E and F are dependent. As we move to the next slide, keep this calculation in mind, as we will discuss some common pitfalls students encounter when working with these types of problems. Common mistakes. First, a very common mistake is confusing dependence with mutual exclusivity. It is a misconception to think that if 2 events are dependent, they cannot happen at the same time. That isn't the case. Mutual exclusivity is a much stricter condition, where the probability of event E intersection event F equals 0, meaning they are physically unable to occur together. Dependence, however, is simply about how the probability of one event shifts based on the other. The 2 events can absolutely happen simultaneously. Second, don't assume that just because events happen in a sequence, they are automatically dependent. Just because event A happens before event B doesn't mean it influenced B. Think back to the example of tossing a coin twice. Even though the second toss follows the first, the outcome of that first toss has 0 impact on the second. That is a sequential process, but the events remain independent. Finally, and perhaps most importantly for your exams, watch out for forgetting to update your sample space. When we are dealing with sampling without replacement, which is the classic hallmark of dependent events we discussed earlier, you must remember to reduce the total number of possible outcomes. If you forget to decrease your denominator when calculating that second probability, your entire calculation will be incorrect. Always ask yourself, has the total number of items in the bag changed? Now, before we wrap up, I want to pause and address some common pitfalls. As we've seen in our marble example, calculating dependent probabilities can get tricky, and it's very easy to fall into a few specific traps. Keep these distinctions in mind as we move into our final summary of the key takeaways. Key takeaways. First, let's revisit our core definition. Remember, we call events dependent when the occurrence of one event directly affects the probability of another event happening. It's that change in the game we discussed earlier. Next, if you are ever faced with a problem and you aren't sure if the events are linked, you can use the mathematical test we looked at in slide 3. You simply check if the probability of E intersection F is not equal to the probability of E multiplied by the probability of F. If that inequality holds true, you have confirmed dependence. To connect this to the concept of conditional probability, remember the conditional link. For dependent events, the probability of F given E is not equal to the probability of F. This is the mathematical way of saying that knowing event E happened has changed the likelihood of event F. Finally, as a practical tip for your exams, keep an eye out for the typical context. Whenever you see the phrase "without replacement" in a word problem, just like our marble example from slide 4, that is your hallmark signal that you are dealing with dependent events. All right, we have reached the end of our lesson, so let's take a moment to wrap everything up and consolidate what we have learned today. That concludes our session on dependent events. Make sure to review the common mistakes we covered in the previous slide so you don't fall into those common traps. Great job today.